Hello, and thanks for clicking on this next Prenoculus production. Today, we're going to be talking about continuity and discontinuity. So this is a concept that you're going to see this year coming up in the next couple sections on rational functions. And then actually, it's a prominent discussion that we have as well when you get to calculus. It's also an important piece there as well. So let's get started by learning the basics of continuity and some discontinuities. So continuity. A continuous function is a function that has no holes, jumps, asymptotes, or gaps. So a lot of the functions that you've graphed before, traditionally, your y equals x squared, your y equals x cubed, square root x, absolute value x, all of those functions were continuous. The ones we just got finished graphing, those power functions, the polynomial functions, they were all continuous. They had no holes, jumps, asymptotes in them, no gaps between one piece and another, nothing like that. All right. In simple terms, a continuous function is one that can be drawn without lifting up your pencil. So obviously x squared you could draw without lifting up your pencil. There's x cubed. You can draw it without lifting up your pencil. Absolute value x you could draw. You could draw a line. But however, if I asked you to draw, let's say a rational function with an asymptote, well, you got to lift up your pencil to get from one side to the other. If you have a piecewise function with two pieces and it jumps, well, you got to lift up your pencil. That's discontinuous. This is a discontinuous function. Okay, if a function is not continuous at a point, it is said to be discontinuous at that point. That's what we're going to be talking about today, types of discontinuities and how to recognize them. Okay, there are three types of discontinuities. The first one is the easiest to recognize. It's an infinite discontinuity. An infinite discontinuity is a vertical asymptote. Infinite discontinuities are said to be what we call non-removable discontinuities. So graphically, you know what an asymptote looks like. There it is. Okay, we would say x equals a is a vertical asymptote, right, of this function. We can also now call it an infinite discontinuity of that function. All right. Equation-wise, where do we look for vertical asymptotes? Well, we try to find the domain. We look for where the denominator is going to come out to be 0 in a fraction. So x minus 4, if we set that equal to 0, we know x can't be 4. And sure enough, if you were to do a little more analysis on it, which we will do coming up, you would find that x equals 4 is a vertical asymptote of this graph. Okay, it's an infinite discontinuity. All right, so look for that denominator, check the denominator, see where the denominator is 0. Wherever the denominator is 0, there could potentially be a vertical asymptote. That's an infinite discontinuity. Okay, the next type of discontinuity is a removable discontinuity. A hole in the graph is a removable discontinuity. So graphically, here's what you see. We have what looks like a line, but literally in the middle of it, there's a hole. All right, so this is considered to be a removable discontinuity, this hole. You can patch the hole. All right, in calculus, you actually learn how to patch the hole. But for now, I need you to be able to recognize it both graphically and as well as with an equation. So in this equation, we can see f of x equals x plus 1 times x plus 2 over x plus 1. Again, first thing I would do is look for the domain. To find the domain, you set the denominator equal to 0. Now, I know some of you might be thinking and looking at that and saying, whoa, 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 you can cancel out the x plus 1s, but not yet. You have to find the domain first, and then we'll worry about that. So x can't be negative 1. Okay, there's a discontinuity there at x equals negative 1. Now, if you go back to what's here, sure enough, you can, in fact, cross out the x plus 1s. You can remove the discontinuity, right? You removed it. You literally took out the x plus 1s. This is where it's discontinuous at -1. You removed it though. So now if I asked you to take -1 and plug it in, you would get, well, your new function now looks like x plus 2. So if I took -1 and plugged it in, I get 1. So what we would say is that there's a removable discontinuity. It's a hole in the graph at the point -1, 1. X is -1, y is 1. And sure enough, there it is. There's that removable discontinuity. There's literally a hole in the graph at -1, 1. Okay? Otherwise, the graph would be the graph of x plus 2, this line with a hole in it. All right? That's a removable discontinuity. Again, all the stuff we're going to practice here coming up after we talk about all three. The third type is a jump discontinuity. So jumps occur normally on piecewise functions. And that probably should, hopefully that makes sense to you, right? If you're working on one piece of the graph for a while, and then all of a sudden you jump up to a different piece or change the piece, right? Change the equation, you might jump from one place to the next. The jump would occur here at the change point, where you change from one function to another. And again, we're going to talk about this coming up toward the end of today's lesson. So even though there is what looks like an open circle here, you'd say, oh, well, there's a hole there at that point. This point is closed in. So literally, you can see we jumped from this curve to that curve at x equals 1. We jumped up. So it's a jump discontinuity. Jump discontinuities are said to be non-removable. Okay? All right. So now let's take a look. And here's a graph. All I want you to do is to identify and classify the discontinuities on the given graph. All right. So first, we can see there's a discontinuity. There's one here at x equals 2. There's another discontinuity here at 4. And then there's a third at x equals 6. So we're going to classify them. These are all breaks in the graph, right? You have to lift off your pencil to be able to graph the rest of it. At x equals 2, that is an asymptote. It is an infinite discontinuity. Okay. At x equals 4. All right, so there's a difference between x equals 4 and x equals 6. At x equals 4, there is a removable discontinuity. Okay, it's a hole there. All right, it's a hole. Okay, now I understand you might be saying, well, wait a minute. I'm on this point here. I have to go down to here. It feels like it's a jump, but it's not considered a jump because once you jump down to here, you jump right back to where you were. So you're still on the same function, the same piece of this graph. It's just at one point you have to jump down. So if I could take this point and put it on this open circle here, I'd literally fill in the hole. So we still consider it to be a removable discontinuity. It's a hole. Okay. However, over here at 6, now this is a jump. This is a jump discontinuity. Okay. And again, why? Because you're on this piece of the graph, and now you jump down to this piece and continue on this piece. You've literally jumped down and continued on this other piece down here. So this is considered to be a jump. So x equals 4 is considered to be a hole. It's a removable discontinuity. And x equals 6 is considered to be a jump because you were on one piece, you jumped down to another piece and continued on that piece. Okay? Those are your difference between the three. All right, now, finding discontinuities algebraically. Infinite and discontinuities and holes can be found by finding the domain of the given function. Find the x values that don't work in the domain, and you have your discontinuities. And then you can go ahead and continue and classify them. Okay? So again, stuff that we've done before. So let's identify and classify the discontinuities of this first function. We have x squared minus 9 over x squared minus 10x plus 21. So what we're going to do is we're going to set the denominator equal to 0, right? That's where I find my discontinuities. So I am going to factor that. I'm going to factor it by 1 a.m. Find me the two numbers that multiply to be 21 and add up to negative 10. That's going to be negative 3 and negative 7. So this will factor as x minus 3 times x minus 7 equals 0. Split them up. I have x minus 3 equals 0. X minus 7 equals 0. I get x equals 7. I get x equals 3. So x can't be 3. X can't be 7. So that means I have two discontinuities. I have a discontinuity at x equals 3 and another at x equals 7. Now, I can't classify them just yet. What I need to do is I need to go back to my original equation. I factored the bottom as x minus 3 times x plus or x minus 7. And now what I'm going to do in the numerator is I'm going to try to factor the numerator and remove any discontinuities that I can. Well, the top factors is difference of two squares, x plus 3 times x minus 3. And now what I'm looking for is I'm looking to remove any of the factors in the denominator that gave me a discontinuity. And sure enough, these x minus 3's, they can be knocked out. So now I know that x equals 3 is a removable discontinuity, which means it's a whole. Okay? My function now says x plus 3 over x minus 7. There's a hole at the point, well, now I can take 3 and plug it into that. So if I plug 3 into my final equation that's there, I get 6 over negative 4, which is negative 3 over 2. So there's a hole at the point 3, comma, negative 3 over 2. Okay? At that point, I'm literally going to put an open circle on the graph. All right. Now, at x equals 7, I could not remove the x minus 7 from my equation at all. It's still there. So this means it's a vertical asymptote. Okay? It's an infinite discontinuity. Okay? It's non-removable. You couldn't remove it. All right? It's still there. It's still an issue. All right? So there's my two discontinuities, and there they are classified. Okay, one more time. We're going to try 1 over x squared plus 7x. So first thing we're going to do is try to find the domain. So set the denominator equal to 0. Take out the x. It's a GCF. I can split them and solve them. I get x equals 0. And then I have x equals negative 7. So I have two discontinuities. One at x equals 0. One at x equals negative 7. So now I'm going to come back up here again to try to classify them. Take the x out, x plus 7. It's factored on the bottom. On the top, there's nothing to factor. So now the question is, can I remove either one of these issues? Do I have an x up here to cancel with this x? No. Do I have an x plus 7 to cancel with this x plus 7? No. I can't remove either of them. So they're both non-removable. These are both vertical asymptotes. They are infinite discontinuities. Okay, and that is the difference between infinite discontinuities and holes. Infinite discontinuities are non-removable. You can't remove them. Holes you can remove. All right, and then you'd be able to then plug the x value back in to figure out what your y value is for the hole. Okay, and then finally, let's talk about those jump discontinuities. Determining jump discontinuities on a piecewise function. So the first question is, what determines the jump? So the fact that this thing jumps means that it was a piecewise function. And the other thing that determines the jump is that the two pieces that you have don't have the same y value at the jump point, right? At the change point. So for example, if my function here is it's changing at x equals 0, right? When x is less than 0, it's the red graph. When x is greater than or equal to 0, it's the purple graph. So this equation is, let's see, it's down to 1 to the right. So negative 2x plus 1, that's the red equation. And then the purple equation starts from -1. So the y-intercept is -1, and it goes up 1, right 1. So x minus 1. So there's my 2 lines there. This is my equation for this graph that's here. Now you can see at the point where the graph changes, literally the change point, where it changes from one graph to the other at x equals 0. If I take 0 and were to plug it in to this top equation, I would get 1. But if I plug it into the bottom equation, I get -1. So literally, the graph is going to have to jump from 1 at the red line, the top line, down to -1 to start the purple line. So you jumped, okay? So when the two y values here don't match at the change point, they're not the same, that determines the jump. So, for example, let's figure out if this function is continuous at the change point. Here's the change point. Here's g of x. It's a piecewise function. Here's the change point at x equals 2. Now, again, I understand I'm not supposed to be taking 2 and plugging it into the top piece, but I just want to see what its y value would be. So if I take 2 and put it in, I get 10. If I take 2 and put it in the bottom piece, I get 10, which means that the y values match up. So what does that mean for me? If I were to graph this, and you can see 3x plus 4, if I go up 1, 2, 3, 4, okay, up 1, 2, 3, 1 to the right, up 1, 2, 3, 1 to the right again, and I were to graph this, where x is less than 2. So that's all I want to graph. And I want to put an open circle there. Now, if I went to then the 5x, that's my first piece. If I went to the other piece, y equals 5x, and tried to graph it, I'd start on 0, go up 5, 1, 2, 3, 4, 5, 1 to the right. Then up 1, 2, 3, 4, 5, 1 to the right. And sure enough, this graph on the bottom, the y value matches the other graph. So they're actually connected. 1, 2, 3, 4, 5, 1 to the right. And then from there, you could actually continue with the graph of y equals 5x. So this function is continuous at the change point. Okay? Because at the change point, they have the same y value. That's what's important. Now, there is more to this. There's no doubt about it. In calculus, you learn a lot of notation that will help you to determine this, whether or not a function is continuous at a given point. But for now, this is enough, at least of an idea. So for h of x, same idea. If I were to take 1 and plug it into the top piece, now I know I'm not allowed to, but I'm doing it just to see what its y value is. It gives me 7. But if I put 1 in the bottom piece, it gives me 11. The y values don't match. They don't match at the change point, which means that if you think about it, at x equals 1, on this top piece, you're going to have a point at 1, 7. It's going to be open. And then on the bottom piece, the point's going to be at 1, 11 up here. So you have to jump to get from one piece to the next. This is discontinuous at the change point. And that's it for now. So again, in calculus, you're going to learn a few additional things about this concept of figuring out if a function is continuous or discontinuous, especially with piecewise functions. But for now, this is at least a start. It's a way to get going. Okay? And as always, thanks for clicking.